All right, sticking with our quadrilateral study here, another kind of parallelogram we're looking at is a rhombus. The plural for rhombus is either rhombuses or rhombi. You can say it either way. They have all equal sides, so they're sometimes known as an equilateral quadrilateral, and that's really all we need to know about a rhombus is that it has all four sides the same length. Once we have that as a given piece of information, we can deduce that it's a rhombus, and then all of a rhombus's properties will apply. So a rhombus is also a parallelogram. We can prove this real quick here. So given that ABCD is a rhombus with diagonal BD drawn, remember, given that it's a rhombus really means all four sides are equal. That's another way of saying that. So why must ABC or ABD be congruent to CDB? So these two triangles, in other words. Well, if we have congruent sides, all four all the way around, then we can say that AB is equal to DC, and we can say that BC is equal to AD. And so those, along with the reflexive property, BD equals itself, we can have a side-side-side congruence here. Therefore, angle 1 is congruent to angle 2 because those are corresponding parts. And anytime two alternate interior angles are equal for another reason, then we can say that the lines are parallel. So that indicates that this is a parallelogram. So opposite sides being parallel and congruent is the property that we're calling on there to say that this is in fact a parallelogram. All right, so other properties that we will come across with a rhombus. If you look at these two diagonals drawn in here in this rhombus, and we use tracing paper to carefully trace triangle RWS, what you should notice is that that tracing paper can be flipped and rotated and translated around the diagram to make it fall onto or map onto all of these other three triangles. So what we end up with is four congruent triangles here. At least that's what the tracing paper shows us. We can prove it, and we will, but that's the way you can see it visually is by tracing one and moving it onto the others. All right, so we saw that with an experiment there. In exercise 3, we can prove it. We can prove that any two consecutive triangles will be congruent in a rhombus, and then we could just extend that proof and do it again with different segments. So if we do it once, we're doing it for all. So starting off with it being a rhombus as our given, we can then say that any of these outer segments are congruent. So if we use RS and RU, since our goal is these two triangles up here, that would make sense to use those two outer sides. We know we have a reflexive segment here at RW, and because a rhombus is a parallelogram, we also know that the diagonal has been bisected, because all parallelograms have that property, no matter how specific they are. So UW is also equal to SW because of that diagonal being bisected. So we have another SSS proof here to show that those two are congruent, and that would have applied no matter which two triangles I chose. We would be able to use the same exact argument with outer sides equal, reflexive segment, and a diagonal being bisected. So that's another property that we can deduce is that we have congruent triangles within a rhombus. So given that diagram above and the fact that the four triangles are congruent, what we can say is, well, actually two things that we can conjecture here. One is that the diagonals are perpendicular, and the other one is that the diagonals bisect the vertex angles. In other words, the outer rhombus angles have been bisected by the diagonals. So if you look back at the diagram here, if angle R, if this RT segment wasn't drawn in yet, angle R would be this obtuse angle, and so would angle T. What we're saying here as a possibility is that RT, this diagonal, cuts angle R and angle T in half, creates two congruent angles here, and that the same thing happens on the other diagonal. We're also saying on the first conjecture that these two diagonals will always form a right angle. So can we prove it? Well, given what we saw that all four of these triangles are congruent, we can say that angle UWR and SWR are equal to each other because they're corresponding parts, right? So these two angles in here at the center are congruent to each other. And also they form a linear pair. That's obvious that they fall in the same straight line SU. So any two angles adjacent to each other on a straight line will add up to 180. And if they're equal and supplementary at the same time, they must be 90 degrees. And we could do that same exact proof with any pair of those central angles. So we do know, in fact, that the diagonals are perpendicular to each other. And to show that they bisect the vertex angles, the same logic applies. It's angle URW and SRW. Those are corresponding parts of those same two triangles we just discussed. And so by definition of bisect, when we have two equal angles, we know that the segment must have bisected the larger one. So those are now two properties of a rhombus that we can always use as well. Okay, and exercise 5 here. If a rhombus has diagonals of length 10 and 24, what's the perimeter of the rhombus? Well, to get at this one, let's go back to this diagram, even though it hasn't been labeled that way. If, let's say that this diagonal here, RT, was the 10 unit, and diagonal US was the 24 unit. Because of the fact that diagonals are bisected in any parallelogram, no matter how specific, we can call those 10, that we can take that 10 unit segment and split it into 5 and 5. And we can take the 24 unit segment and split it into 12 and 12. So that means that all 4 of these right triangles, and I say right triangles because we already talked about there being right angles at the center, all 4 of those right triangles are 5 by 12. And so if we do Pythagorean theorem with any one of them, we will get the hypotenuse, which will be the same all the way around, given that it's a rhombus. So that's what we have here. We have each triangle being a 5 by 12. Put it into Pythagorean theorem, get 13 units, and then the perimeter would have 4 of those 13 unit segments, and so we have 52 going all the way around. All right, last exercise here. Given that ABCD is a rhombus, so again, all 4 sides being equal, with CBD as 67 degrees, which of the following is a measure of BAD? So that's down here. And one thing we know is that if being a rhombus, the diagonal will bisect the outer angle, so we'll have another 67 there. And we also know that being a parallelogram, we have BC parallel to AD, and so alternate interior angles apply. So I have a 67 and another 67. Okay, so another way to get at that is that once I know this angle is 67, being a rhombus with BA equal to AD, I have an isosceles triangle, so there has to be another 67 degree angle for that reason too. So once we establish that, that's 134 degrees, which leaves us with 46 degrees for the final angle of the triangle, regardless of how you show that BDA is 67.